Next topic, structure and functionality of a Java semaphore. And this is kind of fun. We're going to look at sort of the way in which it's designed, and its design is quite fascinating, and you'll see that its design actually applies one of the patterns that you've seen if you've taken the design patterns course, CS 3251. So we'll start with just a quick recap of what is a semaphore and how is it implemented in Java. So Java has an implementation of the counting semaphore variant of a semaphore, which could be used as a binary semaphore by having 0 or 1. And as you can see from the class description, it's a class semaphore that extends object, and we'll see a bit more about it in a second. There's a bunch of synchronization-related interfaces like lock and read-write lock and so on. Semaphore does not implement those. It really doesn't implement anything interesting other than stuff for serialization. The constructor of the semaphore is used, among other things, to indicate what its initial count should be. In other words, what is its initial set of permits? How many permits are we going to give this thing? Just like, how many bottles of Grateful Dead wine do we have? How many Palantiri do we have? How many volleyball courts or volleyballs do we have? That's the permit parameter. You can see it's just an int. Now, this is what's weird. I told you there's a few things that make your mind explode. The value of n here is not a maximum. It's just the initial value. And that often throws people for a loop because they think that n is the maximum value it could be. You can actually increase it, although it's a little weird, but it's possible. There's nothing that stops you from doing it. It's just an indication of the initial value. And if you want to know why on earth they did it like this, you can find out by reading this link. Another weird thing that'll make your mind explode is that the initial count, the initial value for the permits, can be a negative number. You can start the semaphore being basically in arrears, right? Like you've already overdrawn your account. And in that case, that means you've got to acquire the semaphore a certain number of times before anybody else, you have to release the semaphore a certain number of times before anybody else can even acquire it. It's very strange to want to do this, but it's possible. And I just mention that because sometimes people don't realize you can do it that way, even though it's rather odd. Let's focus more on the conventional things, though. Let's talk about its design. The design of the semaphore class in Java applies our good friend, the bridge pattern. And the bridge pattern is used to decouple an interface from its implementations. So you can have the same interface but have different semantics, different implementations. And in particular, the things we're trying to do here is decouple the interface. We want the same interface with both fair and non-fair semantics. So what the heck does that mean? Well, we'll talk more about what it means to be fair and non-fair in a second. From an implementation point of view, keep in mind this is the bridge pattern from the Gang of Four book. Here's what the bridge pattern looks like. You have some so-called abstraction, which in this case is the semaphore class, or an instance of the semaphore class. And then you've got a reference to a hierarchy. And over here, as you can see, this is the implementation hierarchy. It starts with a class called sync, and then we can have fair sync and non-fair sync. And if somebody calls an operation on the semaphore, it simply forwards to the appropriate corresponding operation on the implementation hierarchy. And we'll talk more about that. That should be familiar to you because that's a pattern that we study in 3251. So here's the way the class is implemented. We've got the sync field here. And of course, that's a superclass. So we're going to make the right kind of subclass depending on what the constructor is told to do. There's the sync class itself. The sync class is an abstract static class. What that means is static means it's kind of nested and hidden inside the context of semaphore. Abstract means it's not actually meant to be instantiated, but it serves as the root of a hierarchy of something else that will be instantiatable. And what it instantiates is something called what sync extends is something called abstract queued synchronizer. Abstract queued synchronizer is a class that comes as part of the Java class library, and it's used to provide FIFO weight queues. First of all, FIFO means first in, first out, as I'm sure you knew. So here's a classic example of first in, first out, right? You're standing in line waiting to do something like check in to a kiosk at an airport, or waiting in line to deposit money in a bank or whatever, right? Get food at the commons or whatnot. And so FIFO weight queues, that's what abstract queued synchronizer does. We'll talk a bit more about that later. If you want to learn more about abstract queued synchronizer, take a look at this paper by my buddy Doug Lee. He wrote this code. And then we have a couple of subclasses, namely nonfare sync and fair sync, that extend sync. So notice that nonfare sync extends sync, sync extends abstract queued synchronizer, and nonfare sync is going to override some of the abstract methods in abstract queued synchronizer to do things in a non-fair way. Fair sync is going to override some methods in abstract queued synchronizer in a fair way, and I'll talk in a second what it means to be fair and unfair. And in a nutshell, fair means FIFO and non-fair means non-FIFO, but I'll explain that in more detail. And you'll quickly understand this from everyday life, which I'll show in a second. The constructor of Semaphore allows the person who's creating the object, initializing the object, to select the semantics they want, either fair or non-fair. And how is that done? It's quite simple. There's a Boolean parameter with the name fair, and you might imagine, as we'll see in a second, if the value of fair is true, then we get a fair synchronizer, and if the value of fair is false or not true, we get a non-fair synchronizer. Hey, that's pretty easy to understand, right? And this is just the old ternary operator in C or Java or C++, where you've got, if this condition is true, do this, else do that. So it's kind of like an if-else statement. Other languages like Kotlin don't need a ternary operator because they let if-else statements return values and stuff like that. This is the same pattern used by other Java synchronizers like reentrant lock. We'll talk about that later. And what happens if you select fair sync is you end up with strict FIFO ordering, which is fair, but it comes at the expense of performance. So things may be slower than you might have expected, or you might want. Of course, if you know how things work, you understand that FIFO means fair, but fair doesn't always mean fast. So FIFO just means the order in which things queue up is the order in which they're served. In contrast, non-fair synchronizers give you potentially faster performance, and in practice often way faster performance, at the expense of fairness. And the best way to think about this, that you might be able to relate to, because every culture deals with it and every culture deals with it differently. If you have a bunch of people standing in line and someone cuts in line or butts in line, that's called unfair, right? They get to move up. And some people get very upset about this, other people could care less. It's really fascinating if you go to different airports around the world. If you go to the US, if you go to England, people queue, and they queue pretty much in FIFO order. If you go to other parts of the world, I won't name any names to avoid making people feel on the spot, they do not queue, they bunch. And it's like a madhouse, it's like a scrum. And so when you go to the airport, it's like everybody just rushes up to the front. It's chaos and insanity. And those of us who come from a queuing culture are like shocked at how horrible this is. People who come from a non-queuing culture are like, why are these people who speak English so uptight and they have to stand in line? It's really kind of funny. So the point is that non-fair is faster but not fair. Fair is fair but not as fast. And when you learn how to implement fairness, you'll see why it's not as fast. It's way, way, way slower. By default, if you just use the semaphore that only allows you to have a permit count rather than a Boolean, you get non-fair semantics. And the idea there is, by default, you want performance over fairness. And if you want fairness, you've got to say, I want fairness. So as I mentioned, fair semantics are way, way, way slower. So if you don't need fairness, don't make your semaphores fair. I believe for the implementation you're using for the Palantir simulator, you want fair semaphores. You want them to take turns. So it is set that way. As I mentioned before, you don't always have to fully bracket the acquire and release of a permit from a semaphore. So there's other examples which we'll talk about maybe later today, in fact, to use semaphores to coordinate interactions between threads, where you actually use counting semaphores that are restricted to the values 0 and 1 to take turns doing something. And in that case, the thread that acquires the semaphore is not the same one that releases it, because they're taking turns doing that. Once again, it's not a right or wrong issue. It's just, what is your problem trying to do? And the reason I mention this is that there are other synchronizers, in particular reentrant locks, which we'll talk about when it's time in the class, that are bracketed. You have to use them in a fully bracketed way. And if you have a reentrant lock and you try to unlock somebody else's lock that they own, that's a protocol violation, and you'll get illegal state exception or something like that. Okay, so that's a quick overview of the structure and functionality of a semaphore. You probably still wouldn't be in a great position to program the semaphore. We'll talk about how to do that in just a moment. But hopefully you at least have an appreciation for kind of what it does and how it's designed. And what's cool about this is that little bridge pattern thing we saw, that gets used by a whole bunch of the Java synchronizers. That bridge pattern structure is used by semaphore, it's used by reentrant lock, it's used by condition object, it's used by reentrant read-write lock, and so on. So it's a very common design structure, which is cool because all those things you studied in the patterns course actually get used in practice in things very fundamental like synchronizers in Java.